All right, Corona video 14. Still working on electricity, focusing in on series circuits this time at VHS, the Columbia of the MVL. Last time we looked at some of the basic ideas of a circuit. We talked about the difference between pictorials and schematics and how we can represent these things uh, with a schematic, and it's a time saver, makes it easier to draw a circuit. We also talked about Ohm's law, V equals I times R, and we talked about power, current times voltage. And this is the one we're going to use most of the time. It's going to allow us to unlock the secrets of a circuit. We talked about voltage. I used the analogy of a hand pump, and I talked about moving the lever up and down as the push or the voltage. And then the water flowing through a hose would be the current. And if we kink the hose, that would be considered resistance. We did a little practice problem, and we only had one bulb in our circuit. We talked about the difference between conventional current and the actual flow of electrons. And we also worked a little bit on understanding what a coulomb was, and then how we can use the charge of an electron to actually figure out how many electrons we have passing through something per second. So how are we going to do it differently this time? Well, this time around, what we're going to do is we're going to produce a circuit, and the circuit that we produce, we're going to set it up, and we're going to go through multiple light bulbs. So we're going to have 1, 2, 3 different light bulbs that we're passing through. So we have 3 resistors, in other words. I'm going to use 6 volts again for my battery voltage. And then I'm going to give you the resistance of these light bulbs. I'm going to make the resistance of the light bulbs vary. So these light bulbs would have different wattage, if you will. So let's say that this is a 2 ohm resistor. Let's say that this is a 5 ohm resistor. And then let's say that this one's an 8 ohm resistor. And so what we have to do then is figure out some different things about the circuit. Like, for example, what's the current in the battery? What's the current in the wires? What's the current in this light bulb, and this light bulb? Now, believe it or not, it's not as hard as it might sound. There's not actually going to be 6 different times we have to solve for it. We just have to solve for it once and then realize this is the series circuit. So remember our rule. When we have a series circuit, the current is the same everywhere. Series circuit same current. So just find it once and then you'll have it, okay? So the way this works is we're going to find something called effective resistance. Now the word effective actually means total. So effective or total resistance for a series circuit is pretty easy, in fact. You just add them up. So it's going to be the resistor 1 plus resistor 2 plus resistor 3. And if there were more resistors, we would even do even more of this, okay? 4, 5, 6, as much as you want. So my total resistance in this first example, or effective resistance, would be 2 plus 5 plus 8. So the effective resistance, or total resistance, would be 15 ohms. That's what's going to affect the flow, not the 2, not the 5, not the 8, but the total combined 15. So once we've found that, we can kind of redraw our diagram here. And this time, what we can do, I gotta remember which way I had the battery facing. There we go. So this time, I'm going to just make one big resistor, which is the effective resistance. So if I put 15 ohms here, remember this is a 6-volt battery, and then I run through what the current would be based on this, this is how I'm going to do my calculation. I'm going to say V equals I times R. I'm going to put in the voltage of the battery. I'm going to put in the resistance of everything, and then I can solve for my current, I. So 6 divided by 15 will give me my current, which is 0.4. So I have 0.4 amps going in here. And I also have 0.4 amps going in here, and the wire, and everywhere. So guess what? We can now translate that back here and put in my 0.4 amps here, and here, and here, and here. You get the idea. And here too. Everybody's got 0.4 amps. Okay, once we have that amperage figured out, now it's time to kind of focus in on voltages. So we also need to find the voltages in the different parts of the circuit. Now the voltage in the wire is 0 because there's no resistance. Remember, the wire is ideal. And when the wire is ideal, we can just ignore the fact that it slows any flow at all. So then we have to find the voltages of each individual resistor. So that means Ohm's law times 3. So the first time we do this, we want to put in 2. Then we'll do it for 5. And we also want to do it for 8. So I'm going to be putting in my different currents here, 0.4, 0.4, and 0.4, and running it through. So 2 times 0.4 gives me 0.8. So I have 0.8 of the 6 volts going in here. Here I have 2. So 2 of the 6 go into the 5 ohm resistor. Now because this has the most resistance, it's going to take the most push of the battery. And so we're going to end up getting 3.2 to get through this. Now when we add it all together, check this out, add up the voltages, we get the voltage of the battery, which is why this makes sense. So that 6 volts was distributed, but it wasn't distributed equally. So this is your check to see if you're going to get it right or not. So the 2 ohm resistor had 0.8 volts, this had 2 volts, and this had 3.2. And once again, if we add them up, we get the voltage of the battery. And so this is how you deal with a series circuit. Now the weird thing about this is because they all have the same current, even though they have different resistances, they all glow the same. That's only as long as you don't have any resistance in the wire. If we have resistance in the wire, then you would get something called voltage drop. And each time the battery would become weaker and weaker the longer the wire is. But for our example here, all bulbs are the same in terms of the brightness because they all have 0.4 amps. If you were to unscrew one light bulb, the whole thing would shut down. So to recap, what we did is we found the effective resistance. We did that by just adding them up. We made a little diagram, and our diagram was a little bit different because we just had, oops, there it is, one resistor of 15 ohms, which was a total of the 2, the 5, and the 8. And then using the effective resistance in Ohm's law, we found the current going through everything. Once we found the current going through everything, we were then able to apply Ohm's law yet again and then solve for the voltage. When we added up the voltages, we got the voltage of the battery. So it makes sense. All right. We'll check in next week and talk a little bit about parallel. But if you understand series, then you're doing well.